The talk today is titled Hardware Trojan and Microarchitectural Side Channel Attacks. And I'll show you a bunch of detection and mitigation techniques oriented to the hardware. I like this sentence given by Mark Teranipur saying that usually security experts assume that the hardware underlying the information is secure and trusted. But this sentence has demonstrated that this is not so longer true. What I mean is that just thinking on the business model of the chips, starting from the HDL, starting from the design, going to the synthesis, the placement and the routing, so all those phases happen in different places, in different countries, in different foundries. And this means that at the end of the day, on the system on chip, we have different components which were developed, which were placed there from different companies. And the question is, can we trust them? So the idea is, okay, so let's explore some methodologies to analyze and to detect what's potential malicious activity into microprocessor-based systems. So from the high-level point of view, if we speak about hardware vulnerabilities, we have many of them. Hardware Trojans, counterfeiting, backdoors, reverse engineering, IP piracy, and so on. So I'm gonna focus on hardware Trojans, side channel attacks, in particular with the microarchitectural ones, and tampering, referring to the FPGA bitstream modifications. So, just a few words, what's an hardware Trojan? It is a malicious component, which usually is very little, very difficult to be detected by looking at, that can change the functionality, reduce the reliability, or leak information. So that's an idea. So we can add some gates which were not present in the model, in the safe design, to modify the function, and or we can add components like a capacitor in order to modify the specification. Okay? If you have questions, please feel free to interrupt and to ask whatever you want. So regarding the taxonomy, we have, so there is the Trust Hub repository, which is it's a big dataset containing different models. It's a catalog actually of hardware Trojans, and we can select our model looking for abstraction level or location or effect and so on and so forth. So there are many of them available in this dataset. So just to make some examples regarding hardware Trojans, so in this processor, the C3 given by the VIA technology, it has been found a backdoor. So executing a particular sequence of instructions, the attacker was able to grant permissions and to escalate privileges by just executing a particular sequence of instructions. On the other hand, 2 years ago, a bunch of devices exploded after receiving a message. So it has not been demonstrated, but could we think that this was a kind of trigger, like the sequence of instructions executed in the VIA commercial processor? And actually, the day after, same scenario. So other devices exploded after receiving a kind of message, kind of trigger. So today, in this focus, we'll focus on hardware Trojans that change the functionality of the microprocessor. So the idea, as we were saying before, is to add an hardware module, which runs in parallel to the microprocessor, which will be monitoring on what's happening during, before and during the program run. And the goal is, the idea was to have something which is programmable in order to have something which can be customized. So the overall idea of the first countermeasure dealing with hardware Trojans is the following one. We have a guy which, as I was saying, runs in parallel to the, it's a kind of coprocessor, we can say, which is very lightweight, which is in parallel to the processor, and it works in two phases. In the configuration phase, we specify what's legit, and in the query phase, the hardware module will be monitoring what's happening and will be comparing if what's running is legit and is the same we specified before in the configuration phase. So that's an example, and here we were taking information regarding addresses and instructions. In the first phase, when the user is writing the program into the instruction memory, the hardware security module is taking information regarding legit addresses and legit instructions. Then, during the query phase, the microprocessor is running, so the hardware module will check if the addresses required by the microprocessor contain legit instructions which are coming from the output of the memory. So, just to give you a bit of more details, actually the hardware security module is built on a bunch of arrays, and those arrays are addressed by hash functions, and those hash functions are addressed by 16-bit signals. So in this case, I am saying, okay, I'm writing, so the user space is writing the program and is writing the first instruction. So the hardware security module will split those two big 32-bit values into different chunks. And the first chunk contains the first 8-bit of instructions and the first 8-bit of the address, which are the legit ones. The second chunk contains the second 8-bit of the instructions and the second 8-bit of the address, and so on and so forth. So, hashing this value, we can say, and we can address the location of the array, saying, okay, this occurrence arrived, so we can put one here. This occurrence arrived, and we can put one here, and so on and so forth, for the whole program installed into the memory. Same during the query phase, we'll be checking if we are still pointing here all the ones we were installing and we were writing before. And if there is no, if there is no attack, if everything was correct, we expect to have all ones pointed here. On the other hand, if someone pushes an instruction which does not belong to the required address, so this particular combination was not present during the program installation, sorry. So we'll point at 0 here, so we raise a warning saying this combination of address and instruction was not present before. Just to give you a bunch of rates, so in the threat model number 1, we have an attacker which is pushing whatever is the performance counter value. The attacker is pushing a particular instruction. So we have different implementations of the previous hardware security checker, and we got in this implementation false negative rates. So false negative means an attack which we are not detecting, and a false positive is an attack, a safe run, which we are signaling as attack. So a false alarm, false positive, an undetected alarm, false negative. So in this implementation, we have some false negatives. In this implementation, we have 0 false negative and 0 false positive. The false positive are 0 by the mathematical behind, but yeah, also in this case, in the implementation number 1, we also get 0 false negatives. In this thread model, where the attacker is modifying the performance counter, so the address required to the instruction memory, we have some not negligible false negatives. But in this case, we are saying the attacker is gonna execute a legit instruction, but in a wrong time, in a wrong moment. Before, it was an instruction which was not belonging to the program, into the stalled program. So this is a safe instruction, but in a wrong moment. If we want to increase, actually, if we want to decrease the false negative rate, we could, in parallel, compute, for example, some parity bits, and we can compare, we can consider, in addition to the bit arrays, also the ACC, the ECC, for example. And in fact, in the third implementation, we slowed down the false negative rate for the second thread model. Regarding the hardware, actually those ones are the rates, and we are quite lightweight with respect to the target processor. So this is the overhead in terms of resources in the target RISC-V processor, Palpino in this case, risky Palpino. So far, if we were saying before that via software an attacker could trigger a particular hardware Trojan just executing some particular instructions. Okay? So how can we do to avoid software exploitable hardware Trojan activations? The idea is like having and implementing an obfuscator. Here, in this work, the idea was, okay, can we put something into the processor in between the decode and the execution stage, and this hardware code obfuscator will take the same inputs and will provide the same outputs, but executing different operations. And in particular, in order to create confusion, in order to disable, to break the possibility of to break the chain to trigger the hardware Trojan. So in particular, this hardware module adds register scrambling instructions. So it's, I would say, I like to say that this is a hardware compiler in the sense that being transparent with the user, this guy adds some register scrambling. So at a in a certain point, register 4 becomes register, I don't know, 21. It also adds some XOR instructions in order to keep some values encrypted into the processor. And also, when possible, it is adding some garbage instructions in order to make more confusion. So that's the overview. Like, this is a program run in which in the yellow signs indicate the no modified instructions. The gray signs indicate the move instruction, the register scrambling. The blue ones indicate the instruction, the XORing and the XORing instructions. And the orange ones are the garbage instructions. And in this picture, we have the clock. So we have the time here, and here we have the registers. So we are going to write to those registers, making the normal instructions, okay, the normal modified ones, the register scrambling, the XOR, and the garbage instruction. So in fact here, after a while, register 12 becomes register 30, register 17 becomes register 6, 7, whatever, and register 7 then becomes register 21. So this is some those ones are some percentage of the comparing the unprotected and the protected implementations, and we have the percentage of registers written at least once, the deviation of register write operations, and the time in which the values are stored are encrypted into the registers. So far so good, but if we I mean, it's tunable, so we have to pay in performance, of course. So adding instructions means that we are making the program run bigger. It's tunable, but in some cases for those programs we got an overhead, and those ones are delays. So it's tunable again.
So
yeah.
This obfuscation is
Yeah.
based on some randomness or not?
On some randomness, yes, somehow, yeah. Yeah, like the hardware module is, I would say, smart enough to understand when to do some random things or when to do a mov, when to do, yeah. So yeah, that's the overhead. Okay, now let's focus on the other vulnerabilities, hardware side channel attacks, the microarchitectural ones. So what's a side channel attack? Like it has been demonstrated that looking at side channel features, looking at features that are not strictly related to the program run, an attacker could gain information regarding what's doing the processor. And even without having physical access to the device. And via side channel attack, an attacker could leak information and or inject a fault. So just to pass the message of the side channel estimation, let's do a game. We have two pots, a red pot and a blue one, and we have two numbers. There is no pointer here, no. But we have two numbers, 28 and 10. So can we understand what was can we understand which number was put into which pot by looking at the final result, multiplying by 10 the content of this pot and by 7 the content of this pot? Let's see. If we put 28 in the red pot and we put 10 in the blue pot, we get 296. Okay, the sum is even. What about we put 10 in the red pot and 28 in the blue one? We get 350, which is even too. But the evil is always in the details. In the first, when we get 350, the mental leading is a little bit more easy. So in both cases we get even numbers, but monitoring the time in which the response comes, we could understand which number was put into each pot, because the operation on the left is a little bit more easy. So that's the timing attack, and a very well-known attack is Freshery Road. So the attacker and the victim share the memory. After a while, the attacker flashes one memory line and then waits. After a while, it reloads that cache line, and monitoring the time in which the response comes, the attacker can understand if the victim was using that location or not. Very quick overview regarding the CPU. So we have the instructions which are into the instruction memory, and they have to be fetched, then they have to be decoded, and finally executed. Okay, but come on, we are in a pipeline. We can improve. So we can execute the instruction number 1. Meanwhile, we can decode instruction number 2. Meanwhile, we can fetch instruction number 3, and we are ready to address, and we are ready to put in the process also instruction number 4. So we are pipelining, we are improving performance, of course. But wait a second. Jump addresses are executed here in the execution stage. So if I have to jump, what happens to the instructions which are already in the pipeline? So the thing is, we could do two things. We can stall the pipeline, but again, we are decreasing the performance. Or we can predict something. So we can use some hardware blocks in order to learn when the probability to execute branches, to execute jumps, okay? So far so good, but what happens if the prediction is wrong? The CPU actually, so this is called the speculative execution, but the CPU saves the state, I mean, the values, some data that have been put into the cache remain there, even if the CPU restored to the previous, to another state. And that's the Spectre attack. So, injecting a misprediction, we can inject the processor to put some data into the cache. We are injecting a misprediction, okay? And the CPU will refresh and will roll back to the state, but not to the cache. And that's a Spectre attack. Again, what about if instruction 2 depends on the instruction 3? So actually, this is the read after write. So if we want to read just after writing into a particular register, we have to wait at least 1 clock. We have to wait the write back. So again, can the read after write be a problem? Actually, yes, because without entering into detail of this attack code, but if I monitor the time in which the response comes and I try to increment one by one register to write and then to read, actually monitoring the time in which the response comes, I can understand the value of the target register, because if I increase the address of the register, and if the results come 1 clock after, it means that the pipeline has been stalled. It means that I got the exact value of the address I was checking. Rowhammer. So I don't want to say that Rowhammer is an attack to leak information, but is a side channel injection attack. So in the memories we have cells, and the cells are electromagnetic linked. So if we read write, if we hammer one location, for sure at a certain point we will inject a bit flip in the adjacent location. So the attacker here is exploiting a side channel effect, okay? So we hammer one location in order to induce a bit flip in the adjacent one. Let's now present the countermeasure. Again, same approach. An hardware module in parallel to the processor, which is programmable and which is monitoring what's happening to the run, and then erases a warning. So that's the overall idea. How is this module implemented? So actually we have different modules, 4 modules. The programmable attack module unit, the checking logic, memories, and hash logics. So that's the idea. The hardware module takes the fetch instruction, and then here computing on the OP code, computing the occurrences of this OP code, we are counting how many times those OP codes are happening. And here we have the checking logic. So the checking logic contains the programmable attack module unit. So the user can program and can put which are the malicious OP codes, which are the thresholds after which are the thresholds after those OP codes become malicious, and also we have the timeout limit. So, and let's see how this workflow works. So, at the beginning we flash all the memories. Then we add our fetch instruction. Is our timeout over? Timeout limit specified by the user. Is our timeout over? No. Let's add another instruction. Is our timeout over? No. And let's continue this loop. Once our timeout is over, let's check on the threshold. Have those thresholds been exceeded? No. All good. Let's repeat. Yes. Oh, it's a problem. There is a warning. Okay? So, just to report to you again some hardware resources, different configurations. So here on the left, this number is the number of hash functions. And here on the right, there is the size. So how many bits are containing those cells memory. And yeah, overhead in terms of that out-of-order RISC-V processor, in terms of lookup tables, flip-flops, and so on and so forth. Yeah, in this work, we focused on a bunch of attacks, so 3 versions of read after write, the orchestration, 3 versions of Spectre, 3 versions of Rowhammer, and 3 versions of flash reload. And those ones were the number of instructions executed. We got a bunch of false positives, so false alarms. And those ones were the safe programs. But in this situation, so the best, we can say, having three different memories, 64-bit each, we actually reach 0% of false positives. A bunch of other rates. So here we were detecting orchestration. Here we were detecting Spectre. Here we were detecting Rowhammer and flash and reload. Another idea could be, okay, but if we offline run our attack, can we extract some features in order to implement the final hardware module, hardware security module, including also machine learning models? That's an idea. So offline, we run our attack, and we make our machine learning computations in order to see which are the most important features to monitor in order to implement our hardware guide. And that's the idea. Once we find the best model, we can proceed with the hardware implementation. Yeah. The power of this attack is that if a new attack comes, we can just restart from the beginning. A bunch of rates here of some implementation, so it's a work in progress work. We were targeting and we were implementing a standalone hardware module dealing with the x86 architecture, and those ones were the rates we got. So we find out some features to monitor, and those ones were the rates. False positive, false negative, true negatives, and so on. The RISC-V implementation is ongoing. Yeah, so another idea could be, can we extend, extending this approach using Gem 5. So Gem 5 is a pretty useful simulator in which you can build your custom processor. You can specify, I don't know, the instruction set architecture, you can specify the memories, whatever you want, okay? So You build your custom processor, you execute your benchmarks, and you can extract performance counters. And Gen 5 is pretty useful because after every run, it dumps like more than 1,500, it depends on the version, but more than 1,500 features. Okay, it's not feasible. I mean, there is no microprocessor that gives access to so many performance counters, but that could be useful to understand which are the features which are most important to monitor for detecting those attacks. So this is an idea like with a machine learning random forest, in this case classifier, we were able to detect 100% accuracy without false positive and without false negatives. And those ones are the first 25 features. Okay, this seems maybe too high, but of course it makes sense. We are looking at more than 1,500 features. So it's something which cannot be feasible into a real system. But maybe looking at those features, so all of them are related to the RAM, so we can go implement in the hardware module. So far, so good. If there aren't any questions, I can go discussing a bit another threat model. Yes?
Yeah, I'm a little bit lost. Because I don't really understand what the meaning of detecting one particular kind of attack and what is the real interest of that.
In the sense that we were, I mean,
maybe my question is, what is the generality of when you say, okay, we'll detect V1 or
yeah?
What's the meaning of that? It's just for...
It's a use case.
Yes, but you detect a particular, the execution of one particular code that will execute a V1 attack, or any kind of V1 attack? What is the generality of it?
Yeah, it could be a generality. I mean, here you are, we were just saying we can run the attack we want to detect. We can implement our machine learning model in hardware to detect them. And then in this case, like maybe here also, yeah, we were nesting some attacks into real programs. So we made some experiments considering some attacks and some safe benchmarks. So those, I'm reporting use cases, but in theory, this methodology could be extended to any attacks.
Could you comment on which benchmark are you using precisely?
Earthsort, Cormark, Towers, Median for this implementation. For this implementation, for the hardware Trojans, there were some other... those ones. Yeah. Those ones here for Spectre, Earthsort, Cormark, Towers, and Median. So we were nesting those ones in this application. In this other application, we were looking at different types. So crypto ones, networking ones. I have another slide, but here there is not a table with all the benchmarks, but I can retrieve it. No, this is not my computer. But later I can show you which were the benchmarks we were referring here.
But the code that you showed in the previous slide, is this victim code or is this the
attacker code?
And which is the victim then?
The victim was running his safe benchmark. So in parallel, I mean, that's an example. That was an example. So we were, the attacker was nesting that attack in parallel to the attacker was trying to steal some values from the victim run.
But did you know if the attacker succeeded? Because it's
yes.
to craft how the flash and reload will work with different victims. So if you run, you know, the attacker and the victim, you will see the leak.
Yeah.
But if you just take any victim, it will not work.
No.
Did you test that it was actually leaking?
Yes. It's the previous one is a IVLSI IEEE transaction. So it's, if you want, I can give you all the details you want. So if there aren't any other questions, I can move on this other vulnerability. So can we, machine learning looking, can we detect if my FPGA has been tampered, if my bitstream has been tampered? Yes, and we have access to some features. So during the RTL design, as you can see here, during the RTL design, we have the layer netlist from which we can extract some features. So after simulation with benchmarks, we have performance features, software ones. On the other hand, here we have implementation features, low-level ones. In particular for this work, we were focusing on those high-level features and those low-level features. And we were considering different attack models, and in the end, different hardware for different, in particular, attack models. And it turns out that those ones were the most important features to monitor, to detect hardware Trojans into FPGAs. And of course, it makes sense that the hardware-related features are more important for detecting those attacks. If we make, if we consider maybe just only the performance counters or just the performance counter and flip-flops, we have different detection rates. The question is, cannot we detect hardware Trojans just looking at software features which seem to be very far from the hardware? Well, here not, but here yes. Again, Gen 5. Why? Because again, Gen 5 gives you access to several performance counters. So if we look at the right performance counters, we can detect hardware Trojans into microprocessor-based system. So that's a purely software implementation. So in Gen 5, again, we first build our benign processor. We execute a bunch of benchmarks to extract several performance counters. And once we are good with the benign implementation, we go back. We went back to implementing the attacked processor, so simulating the hardware Trojan behavior into the Gen 5, because Gen 5 we can build our custom processor. And again, we run benchmarks, we extract the performance counters, and finally we give all those samples containing several features to our machine learning classifier in order to see if that CPU, that run, was on a safe CPU or an attacked, on a tampered one. And again, in particular in this scenario, we were implementing this attack model taken from TrustHub. So an attacker which is able to inject, which is able to modify which is able to push an instruction which does not belong to the program. And those ones were the most important 25 features. Again, perfect accuracy. Again, of course, we are looking at so many performance counters. A bunch of open research questions I have, and we can discuss on them. Can we design an end-to-end tool chain bringing feature extraction, machine learning driven feature selection, and hardware implementation of a runtime hardware security checker? Can we build a kind of tool that permits this thing? Can we identify some features which are discriminative for malicious behavior. Maybe there will be some features most related to some transact execution variants or software-induced attacks. Can we somehow rank? Can we make a ranking of those features? Something else, how the machine learning models to detect those attacks are resistant to manipulations. Like if an attacker is able to inject something else, can he modify the performance counters in order to fool the machine learning? Can the machine learning be fooled by the attacker when the attacker is executing the attack and something else in order to fool the machine learning? And another question, I showed you before code obfuscator dealing with hardware Trojans, and that hardware module was making noise. Can we make noise and inject noise to an attacker which is side channel looking in order to prevent the side channel attack? Those ones were some open research questions, a bunch of references if you want to look closer and if you want to have more details. But if you have questions, please ask.